Have you ever been intrigued by how your computer manages memory? It's quite a fascinating process, and today, we're diving into it. Memory management is one of those silent yet crucial aspects of computing that keeps our systems running smoothly. It's the unsung hero that makes multitasking possible and ensures that our software runs efficiently. One of the most prevalent techniques used in this realm is paging. This method, used by operating systems, deftly manages the allocation of memory to processors. It's like a skilled conductor, seamlessly orchestrating the performance of an entire symphony, ensuring that every note, every instrument plays its part at the right time. Paging plays a vital role in implementing virtual memory, allowing the operating system to provide an abstraction of a larger memory space than what is physically available. So, ready to unmask the mystery behind paging? Let's dive in. Paging is a memory management scheme that enables the efficient use of memory. It's all about breaking down memory into manageable pieces, known as pages. This technique is vital to the concept of virtual memory, allowing an operating system to create the illusion of a memory space larger than what's physically available. Now, let's get into the nitty-gritty of paging. Memory, both physical and virtual, is divided into fixed-size blocks. We call these blocks pages in the virtual memory space and frames in the physical memory. Then there's the page table, a data structure the operating system uses to keep track of which virtual page corresponds to which physical frame. It's like a map, guiding the system from the realm of virtual memory to the land of physical memory. And remember, each process gets its own virtual memory space, which is usually larger than the actual physical memory. So how does this all come together? When a process is created, the operating system sets up a page table for it, establishing the crucial mapping between virtual pages and physical frames. The operating system then keeps this page table updated as the process requests and releases memory. Now, let's talk about page faults. These occur when a process tries to access a virtual page that isn't currently in physical memory. In response, the operating system has to fetch the required page from secondary storage, typically a disk, and load it into memory. And what if physical memory is running low? Well, the operating system can move some pages from memory to disk, making room for others. This process is known as swapping. Finally, there's the magic of address translation. This is where the hardware, usually through a memory management unit, translates the virtual addresses to physical addresses using the page table. This all happens behind the scenes, unbeknownst to the process. So paging, in essence, is a memory management technique that provides isolation, prevents fragmentation, and enables efficient use of memory resources. With this foundation, we're set to explore how paging works. Paging isn't just a concept, it's a complex yet elegant dance that your computer performs every time it needs to manage memory. Let's take a closer look at the intricate ballet of paging. Picture a newly created process. The operating system steps in, creating a page table for this process. This table is a roadmap mapping the virtual pages to physical frames. Next, we have the page size. This is a standard measure, typically around 4, 8, or 16 kilobytes. It serves as a yardstick determining the granularity of memory management. When the process makes a memory request, the operating system allocates virtual pages. These pages are then mapped to available physical frames. This mapping is like the seating plan at a grand banquet, ensuring every guest, or in this case every byte of data, knows where to go. But what happens when a process tries to access a virtual page that isn't currently in physical memory? This is where the drama of the page fault comes into play. A page fault is like a call to action, prompting the operating system to fetch the required page from the wings of secondary storage, usually a disk. With the stage getting crowded, the operating system may need to free up some space. It does this through a process called swapping, moving pages from the physical memory to the disk. This is like a quick costume change backstage, allowing the performance to continue smoothly. Now let's talk about the magic trick that makes this all possible: address translation. This is performed by a special piece of hardware called the Memory Management Unit, or MMU. The MMU takes a virtual address and, using the page table as a guide, transforms it into a physical address. This translation happens behind the scenes, seamlessly and invisibly to the process. Finally, the operating system maintains and updates the page tables. This is the stage manager's role, ensuring the correct mapping and efficient use of memory. As processes allocate and deallocate memory, the operating system adjusts the page tables accordingly, keeping the performance running smoothly. So there you have it. That's the dance of paging. It's a complex choreography, but when it's performed well, it ensures efficient use of memory, minimizes fragmentation, and provides each process with its own private and secure memory space. With such a system in place, paging offers numerous benefits. Let's see what they are. Paging isn't just about managing memory, it's about doing it efficiently and securely. This memory management technique offers several key benefits that are crucial to the smooth functioning of any modern operating system. First up, process isolation. Each process in a system has its own virtual memory space, courtesy of paging. This isolation ensures that one process can't interfere with another, providing a layer of security and stability. It's like giving each process its own private playground, where it can run, jump, and play without bumping into others. Next, we have the prevention of fragmentation. Memory fragmentation, particularly external fragmentation, can be a real headache. It's like trying to fit a square peg into a round hole. It just doesn't work. But thanks to paging, memory is divided into fixed-size blocks, or pages, minimizing the possibility of fragmentation. It's a neat, organized system where everything has its place. Then there's the efficient use of memory. In a world where resources are finite, efficiency is the name of the game. Paging allows multiple processes to share the same physical memory, optimizing its usage. It's like carpooling for processes. More passengers, same car. Finally, the crowning glory of paging, the implementation of virtual memory. Paging allows processes to use more memory than is physically available through a mechanism called swapping. It's like having an extra suitcase you can dip into when your main luggage is full. This swapping between physical memory and disk storage creates the illusion of a memory space that is larger than the actual physical memory. But remember, like any other system, paging is not without its challenges. It requires careful management and overheads, especially for page table management and handling page faults. However, the benefits it brings to the table, process isolation, prevention of fragmentation, efficient memory usage, and virtual memory implementation, far outweigh these challenges. As we can see, paging is a fundamental player in the grand scheme of memory management. So the next time you're multitasking on your computer, remember, there's a lot going on behind the scenes, all thanks to paging. Today we've journeyed through the world of paging, a vital aspect of memory management in computer systems. We've delved into the heart of your computer, unwrapping the layers of abstraction that allow it to function so seamlessly. We began by exploring the concept of paging, a technique that divides both physical memory and a process's virtual memory space into fixed-size blocks called pages. This systematic division of memory into manageable units simplifies memory management and enables efficient use of physical memory. We then looked at the page table, a crucial data structure maintained by the operating system. This table serves as a map, guiding the translation of virtual pages to physical frames. Each process has its own virtual memory space, typically much larger than physical memory, and the operating system manages the mapping between these two entities, providing an abstraction layer that simplifies memory access for individual processes. Next, we examined how paging works in practice. We discussed how the operating system creates a page table for each process, how it handles memory allocation requests, and how it deals with page faults. We also touched upon the process of swapping, which allows the operating system to free up physical memory by moving pages to disk, and the role of the memory management unit in translating virtual addresses to physical ones. Lastly, we highlighted the benefits of paging. By providing each process with its own virtual memory space, paging ensures process isolation and security. It also prevents external fragmentation, allowing for a more efficient use of memory resources. Furthermore, paging facilitates the implementation of virtual memory, enabling processes to use more memory than physically available through disk swapping. And so we've come full circle in our exploration of paging, from its basic concept to its practical implementation and benefits. This journey has taken us deep into the inner workings of computer systems, revealing the intricate dance of memory management that underpins our everyday computing experiences. With this newfound knowledge, you're one step closer to understanding the intricate workings of your computer. Thanks for joining us on this exploration of paging.